Assalamualaikum warahmatullahi wabarakatuh and hello everyone. Okay, we continue our lecture into inductive sensor. Alright, so we already discussed potentiometric sensor, which is depend on the value of resistance, and capacitive sensor, which is depend on the capacitance sensor. Now we look into the inductive sensor, which is it will depends on the value of inductance. Alright, so inductive sensor actually is a device that use the principle of electromagnetic induction to detect or measure object. Okay, so how it measure the object? An inductor, it develops a magnetic field when current flow through it. So alternatively, it will flow. Current will flow through the circuit containing an inductor when the magnetic field through it changes. So this effect can be used for us to detect metallic objects that interact with a magnetic field. Non-metallic substance such as liquids or some kind of dirt do not interact with the magnetic field. So an inductive sensor can be operated either in wet or dirty condition. So another one of advantage of inductive sensor is it is a non-contact measurement of displacement, distance, position, oscillation and vibration. So they do not contact with the object. So they are very it's suitable when we need to make a measurement with high precision in harsh industrial environments such as pressure, depths or high temperature. Okay, so how the working inductive sensor working principle? It can be a magnetic flux coupling between two coils can be changed by the movement of an object and subsequently convert it into voltage. Okay, so the basic arrangement of induction, it must have two coil. So which is first we call is a primary coil and second is we call it secondary coil. So from this oh no, okay, so from this figure this one is primary coil, this one is secondary coil. So the primary coil usually carries a certain voltage, which is we call as a V reference, that induce a steady AC voltage in the secondary coil. It induce the voltage in the secondary coil. Alright. So the induced amplitude will on the secondary coil will depends on flux coupling between this coil. Okay. So it depends on the value of magnetic flux. So for induction, it will depends on the value of magnetic flux, right? So we have two technique where we can change the value of magnetic flux. So one is the movement of object made of ferromagnetic material within the flux, which is we move the object within the within the flux path. Okay, so here is the flux path. Okay, so if we move object right and left, okay, so we will change the flux within the between the coil. Okay, so when the value of magnetic flux difference, there will be the magnetic field also difference. Okay, so it will affect the value of output voltage. Alright. Again, another one is one already I mentioned is we move the object the ferromagnetic material. The second one, how we want to change the value of magnetic flux, we can change either what we call the distance between the coil. Okay, we move one coil to another one. So if the distance between that one is difference, they will make change into the output voltage. Alright, so we need to refer to the equation of the magnetic flux. Okay, so actually this is the basic operation for LVDT, which is linear variable differential transformer, or RVDT, rotary variable differential transformer, and the mutual inductance proximity sensor. Okay, so if we look at here, this is a simplified circuit diagram of an interface for an LVDT sensor. LVDT is a transformer with mechanically actuated core. Okay, so the primary coil is driven by a sine wave. Okay, so this is a sine wave. Okay, they have amplitude. Okay, the sine wave eliminates error-related harmonic in the transformer. So an AC signal is induced in the secondary coil. Okay, this one is the primary coil. This one is the secondary coil. Okay, so if you can look here, this one is the ferromagnetic material. Okay, so a ferromagnetic material will be inserted into the cylindrical opening without physically touching the coil. Okay, so the two secondaries are connected in the opposite phase. Okay, when the core is positioned in the magnetic center of the transformer, the secondary output signal cancel and there is no output voltage. Okay, so if the ferromagnetic material is put in the centers, the output voltage will become 0 volts. Okay, so if we moving the core away from the central position, make it unbalance the induced magnetic flux ratio between the secondaries, so there will be developing an output voltage. So if we change, means we make a displacement we are within the magnetic flux, so there will indicate some value of voltage. So the indication of voltage means there is it makes measurement of the displacement. So as the core move, the reluctance of the flux path change, hence the degree of flux their coupling depends on the position of the core. So at the steady state, the amplitude of the induced voltage will be proportional in linear with the operating region to the core displacement. So the LVDT also provide the direction as well as the magnitude of the displacement. So the direction is determined either by the phase angle between the primary voltage and the secondary voltage. So advantage of if we use LVDT and RVDT, first of all, I already mentioned that it's a non-contact device, that it has very little friction resistance with small resistive force. So second, hysteresis, which is magnetic and mechanical are negligible. Third is the output impedance is very low. 4 is there is low susceptibility to noise and interference. 5 is construction is solid and robust, and 6 is infinitesimal resolution is possible. Alright. So I think that's all for inductive sensor. I will show you another video on the Google Classroom for your better understanding. Okay, see you on the next video. Thank you.